Hello, everyone, and a warm welcome to the module on chemical transformations in aqueous solutions. Water is the most abundant liquid on our planet. It covers nearly 2/3 of Earth's surface, and this simple substance has played a key role in much of Earth's evolutionary history. Life almost certainly originated in water, and the need for water by all forms of life has shaped diverse biological structures. In fact, most of the mass of our bodies consists of water, with a composition similar to seawater. The chemical reactions essential for life occur in water, and hopefully, by the end of this module, you'll be able to identify what happens when a substance dissolves in water. We will begin by considering how chemical formulas can be used to write equations representing chemical reactions. Next, we will examine whether substances dissolved in water exist as ions, molecules, or a mixture of both. We will identify reactions in which soluble reactants form an insoluble product, also known as precipitation reactions. Additionally, we will explore reactions where protons are transferred from one reactant to another, and you will learn some basic concepts about acids and bases. Finally, we will examine reactions involving the transfer of electrons between reactants, and you will learn to identify these transformations as redox reactions. A chemical reaction involves the rearrangement of atoms in a sample of matter. Examples include the rusting of iron and the explosive reaction of hydrogen and oxygen gases to produce water. A chemical equation uses chemical symbols to represent what occurs during chemical reaction. We have already seen how chemists represent elements and compounds using chemical symbols. Now, we will examine how chemists represent chemical reactions using chemical equations. A chemical equation represents a chemical statement. When you encounter a chemical equation like the one presented here, you may find it helpful to read it as though it were a sentence. For example, you can read this chemical equation as ammonia and hydrogen chloride react to produce ammonium chloride. Below, you can see another example, which can be read as calcium carbonate react to produce calcium oxide and carbon dioxide. In this context, the plus signs can be interpreted as the word and, while the arrows represent the phrase, react to produce. In addition to interpreting chemical equations, you must also be able to write chemical equations to represent reactions. For example, the equation for the process in which sulfur and oxygen react to produce sulfur dioxide is written as shown here. Similarly, we write the equation for the reaction of sulfur trioxide and water to produce sulfuric acid as presented below. Each chemical species that appears to the left of the arrow is called a reactant. Reactants are substances that are consumed during the course of a chemical reaction. Each species that appears to the right of the arrow is called a product. Products are the substances formed during the course of a chemical reaction. Chemists typically indicate the physical states of reactants and products using italicized letters in parentheses following each species in a chemical equation. Gases, liquids, and solids are labeled as G, L, and S, respectively. Additionally, chemical species dissolved in water are referred to as aqueous and are labeled AQ. In some cases, the physical state must be expressed more specifically. Carbon, for example, exists in two different solid forms, diamond and graphite. Rather than simply writing carbon with S in parentheses, we must specify the form of solid carbon by including either diamond or graphite in parentheses. Please note that some problems in this module can only be solved if the states of reactants and products are specified. In general, it is a good habit to include the physical states of reactants and products in the chemical equations you write. Chemical equations are also used to represent physical processes. For example, the dissolution of sucrose in water is a physical process that can be represented by the following chemical equation, where sucrose is shown with its molecular formula, C12H22O11. Here, The molecule of water over the arrow in the equation denotes the process of dissolving a substance in water. Although formulas or symbols are often omitted for simplicity, they can be written above the arrow in a chemical equation to indicate the conditions under which the reaction takes place. For instance, in the chemical equation shown here, the symbol delta indicates that heat is required to make potassium chlorate react to form potassium chloride and oxygen. Based on what you have learned so far, the chemical equation for the explosive reaction of hydrogen gas with oxygen gas to form liquid water is shown here. However, as written, this equation violates the law of conservation of mass because 4 atoms react to produce only 3 atoms. The equation must be balanced so that the same number of each type of atom appears on both sides of the reaction arrow. Balancing is achieved by adding appropriate stoichiometric coefficients to the left of the chemical formulas. In this case, we write a coefficient of 2 to the left of both hydrogen gas and water to balance the equation. There are now 4 hydrogen atoms and 2 oxygen atoms on each side of the arrow. Always remember that when balancing a chemical equation, only the coefficients preceding the chemical formulas can be changed. The subscripts within the chemical formulas must not be altered. Changing the subscripts would change the chemical identity of the species involved in the reaction. For instance, altering the product from H2O to H2O2 would result in equal numbers of each type of atom on both sides of the equation. But the equation we set out to balance represents the combination of hydrogen gas and oxygen gas to form water, not hydrogen peroxide. Furthermore, we cannot add reactants or products to the equation for the purpose of balancing it. Doing so would result in an equation that represents the wrong reaction. The chemical equation must be made quantitatively correct without altering its qualitative chemical statement. Balancing a chemical equation often involves a trial and error approach. You may find yourself changing the coefficient for a particular reactant or product, only to adjust it again later in the process. To make the balancing process easier, consider the following guidelines. First, adjust the coefficients of compounds before modifying those of individual elements. Next, treat polyatomic ions that appear unchanged on both sides of the equation as single units, rather than counting their constituent atoms individually. Lastly, carefully count atoms and polyatomic ions, and keep track of their numbers each time you modify a coefficient. Now, let me demonstrate how balancing works using a relatively complex example involving the combustion of a hydrocarbon called butane. Combustion refers to burning in the presence of oxygen. The combustion of hydrocarbons always produces carbon dioxide and water. To balance the chemical equation for the combustion of butane, we first take an inventory of the number of each type of atom on both sides of the arrow. Initially, there are 4 carbon atoms on the left and 1 on the right, 10 hydrogen atoms on the left and 2 on the right, and 2 oxygen atoms on the left with 3 on the right. As a first step, we place a coefficient of 4 in front of carbon dioxide on the product side. This updates the tally of atoms, as shown below. Thus, the equation is balanced for carbon, but not for hydrogen or oxygen. Next, we place a coefficient of 5 in front of water on the product side, and tally the atoms on both sides again. Now, the equation is balanced for both carbon and hydrogen, leaving only oxygen to be balanced. There are 13 oxygen atoms on the product side of the equation, 8 in the CO2 molecules and 5 in the water molecules. To balance this, we need 13 oxygen atoms on the reactant side. Since each oxygen molecule contains 2 oxygen atoms, we place a coefficient of 13 over 2 in front of oxygen molecule. With equal numbers of each kind of atom on both sides, the equation is now balanced. However, it is standard practice to use the smallest possible whole number coefficients. By multiplying each coefficient by 2, we eliminate the fraction, resulting in a final balanced equation with whole numbers. Note that a balanced equation is mathematically equivalent. Multiplying or dividing all coefficients by the same factor does not affect its validity. To sum up, in this lecture, you have learned that chemical reactions are represented by chemical equations. Substances that undergo change are called reactants and are written on the left side of the equation, while substances that form are known as products and appear to the right of the reaction arrow. You have also learned that chemical equations must be balanced in accordance with the law of conservation of mass. The number of atoms of each element in the reactants must equal the number in the products. In the next lecture, we will begin examining the types of chemical transformations that occur in water. You will learn about electrolytes, non-electrolytes, and precipitation reactions in aqueous media. Thank you for your attention.